motion looking.
Is some Google Classes or
Yeah, Google Classroom, call it.
are those safe classes or sunglasses?
Or I like to call it the Google. And this PowerPoint, most of this is going to be on the PowerPoint. I'm going to be gone tomorrow. So you're going to be working on this worksheet. If you're done with that, I got a cool idea. Soren's been working on this, looking it up for me a little bit. And we're looking at making belt buckles in here. I think it'd be kind of cool. I want a homemade belt buckle.
We gotta make one like six. So you gotta. We gotta make.
Well, I'm looking at aluminum trash can tops.
Oh,
And then we can take them and then make
Oh,
you know, that's just,
Instead of having watches on your hand,
off the street.
you could put like
there we go. They might be, yeah, there we go. I mean, that'd be easy enough. But so what we're going to learn today is basically if we were going to take a trash can top, aluminum, or a sewer top that Tristan was saying, we were going to have to set different speeds and feeds for that. And how we determine that is basically what we're going to have up here. This is just a small, minute amount. And some of this, honestly, you don't have to do. The computer does it for you. You put aluminum, you figure out speeds. The only thing is sometimes, and we have found this to be true because we didn't check our speeds and feeds that the computer had, and we burned out a bit. So it happens. So in this lesson, we already talked about these, right? Yesterday when we were in the lab. What do we call this? Anybody know? Ball and mill. End mill. This is a 2-flute, 4-flute, and that's a shell cutter.
It's how you dehusk an egg.
Indexable, and so you have indexes that you can put the carbide tips in and take them out. Ethan, can I have you put your phone away, please? So now this is a combination drill and countersink, which the countersink is if you look here and you see how these screws fit nest nicely against here, that's a countersink, okay? And that's this part right here, that angle. And this would be where the drill. And you would use this to kind of start a hole, and then you can come in with an actual drill bit right there. Oh.
What's a spotting bit for? Isn't that to start the hole?
A spotting drill, it's used sometimes where you might not have that, and you just want to be able to just go in and drill, depending on the material. And I don't think so, but you could be right, actually. I don't know. I've never used a spotting drill, so you might be right. Countersink, we use this to engrave the tip, and then we also use the 45-degree edge to do the chamfer on the sides. Flutes, we got 2 flute, more room for chip evacuation. This works better for aluminum, okay? Because aluminum gets a little bit sticky when it gets hot, and the friction creates that heat, and then it'll stick to that tip. So we want that space. And it's used for light metals. They're not great for steel. That's why you have a 4-flute end mill. So you got 4 cutting edges. Chips can be real small, and excuse me. And it's used for harder metals like steel, hardened steel. Tristan?
When the bit clogs up, but the mill doesn't know that, it just keeps going.
Yeah, the mill doesn't know that. And all of a sudden you'll start making a noise, and you're like, that's an unusual noise that mill's making. And then all of a sudden, it just starts getting louder and louder. And I'm like, I think we better shut that off. And then you take it out and it's like caked on there. So, center versus non-center cutting, as you can see here. That's got a piece on the center. If we come here, it doesn't have. And it's continually moving, so it's fine. Yeah, I don't know enough about this, honestly, because this right here, I don't see anything. Maybe I guess this goes to the center where these don't, and there's just an edge, and because they're constantly moving, that you're going to be taking those chips. If we look here, just so we can kind of get an idea, this is right here, the shank. So you can see a 3/8 shank, a 1/4 inch right there. There's 2 high-speed steel HSS, single end mill for cutting aluminum. This is a ball end mill, 3/8 shank, countersink, and then combat drill and countersink, spotting drill. We're gonna watch this video. I gotta go back to.
I thought you already ordered my 2 of those.
Several angles are important when introducing a cutting tool's cutting edge into a rotating workpiece. Those angles include the angle of inclination, which when viewed from the side or front, is the angle of the insert seat or pocket in the tool holder from front to back. The angle of inclination may be positive, negative, or neutral. The cutting tool's rake angle is the relation of its cutting edge to the cut itself, and may also be positive, negative, or neutral. The effective rake is a combination of the tool holder's angle of inclination and the rake built into the insert. The largest influence on chip flow in turning is the top or back rake angle. Viewed from the side of the tool holder, this is the angle created by the top of the cutting tool and an imaginary line drawn horizontally through the workpiece diameter. A positive top rake tool cuts freely with reduced power requirements and reduced temperatures. A negative top rake tool is generally stronger, but it generates more force and requires more power. A negative or a neutral top rake is preferred for rough turning operations, particularly for cast iron.
All right, that was interesting.
Negative cast iron.
Sure.
All right, so if we look at that, I'm not looking at turning you into machinists so that you and expecting you to memorize all this stuff. But what I do want you to know is that there's difference in that, and that you can look it up, find out what we need to know a rake angle is for, or what would be the right or the correct rake angle for what it is that you are cutting. All right, some definitions. Cutting speed, the rate of a tool measuring the surface feet per minute. Okay, spindle speed, the number of revolutions per minute that is made by the cutting tool of a machine. So in that mill, how many times that is spinning around, revolutions per minute, that's the spindle speed. Cutting speed is the rate of a tool measured in the surface, so how fast it's going And then the feed is the distance advanced by the cutting tool along the length of the work for every revolution of the spindle. So every time that spins, how fast can we be moving? Our machine, since it's an educational tool, can only go, I think it's 5,000 something. And that's the max. And a guy that was helping me was kind of getting going nuts because it's like, God, it's really slow. And I think that was the spindle speed. You can only have the spindle speed set at 5,000. I can pay an extra amount of money to get it to turn it up, but not going to do that. You know, because for what we're doing, we're not.
I feel like it's in the software. We should do the modification ourselves.
Let's not break. Let's not try to hack into our $40,000 machine.
What's the worst that can happen?
Not be able to use it. Yeah. All right. So we have cutting speed, spindle speed, feed. Okay. Spindle speed formula. All right. We're gonna this is what. Okay. Why does it keep doing this? No, I don't want this. This is what you want. Okay, N is the spindle speed. So do write this down. N equals spindle speed in RPM. CS is cutting speed. And small d is diameter. Okay? So spindle speed equals cutting speed, which we can typically look up if we know the material, times 12 inch per foot or pi times diameter. There's another formula that I'll show you later on that's simpler than this. You'll find it in Google Classroom. So. And now the circumference of a circle, of course, is all the way around the outside, right? So it's found by dividing the cutting speed by the circumference of the tool.
We should have that as TS instead of this CS for tool speed. So we don't get confused.
All right, don't write this down. You'll have this. You can look it up. But one thing I want you to know, and this does change on the type of bits you're using. So this isn't, this is a rough guideline. Okay, but as we move down, what are we noticing?
The cutting speed.
Okay, so lower number. Yeah. What type of metal is it or material? Harder. Okay. So magnesium is very soft. All the way down to high magnesium steel, titanium.
Alloys.
Okay. So hard alloy steel compared to, soft cast iron. And note, double speeds for carbide cutting tips, okay, which is what you see, but there's no reason for us to have carbide cutting tips because you end up ramming them into something at the wrong speed and you just paid way too much money. But if you're getting so that you've tried it, you used it, and we're going to make 50 of these things, it'd be worth investing in carbide steel or carbide cutting tips so that we could do that. Okay. What spindle speed should be used to mill aluminum with 1-inch end mill? So we looked at that. That's what we have. We'll be doing this. Okay. So spindle speed, right? Cutting speed, diameter. So we know that it's aluminum, cutting speed, 250. So put that in, and what is our answer? You can use I have some calculators if you need, but also you can use your phone. What would the answer be for this? You had to figure out your spindle speed. And make sure if you wrote the formula down that you know that N equals spindle speed, CS is cutting speed, D diameter, right?
Yeah.
So what do you got?
It's about 2000.
Come on. Right there. Okay, and we're not, yeah, that'd be close enough.
You got the right answer.
All right, what spindle speed should be used? Mass with brass. So let's take a look. What is the cutting speed of brass? 150. So 150 times 12 divided by pi times diameter. Pi times, what do we got?
2300.
Well, cutting speed, oh, that's good to know. There we go. This is actually supposed to say brass. And they should do this first before, but I knew going through it that, yeah, we already did this.
This is a nice slideshow.
I know.
Thank you.
Stuck in a looping programming.
It's in a loop.
They actually just have multiple pages of the
What?
same thing. And there's just an empty page.
Well, we already did this, am I right?
Yes.
Yeah, there's a bunch of pages of the same thing.
All right, calculating feed rates.
Yeah.
Okay, FM is feed rate in inches per minute. FT
What is feed?
equals feed in tooths per revolution. So if we have a two flute, how many tooths per revolution? Two. It's four flute. It's four. Okay. Okay. I'm not quite understanding this. Because the number of teeth on the tool would be,
I think you just have teeth in the tool just thrown into two parts of the equation. Even though
all right, well, let's see.
just simplify it.
All right,
You can just get rid of.
so we look at this. We have face mill, end mill, and they have different tool feeds. Okay? Again, double for carbide. So calculate the feed rate for end milling aluminum with a two flute, 1/2 inch high speed end mill.
Oh my god.
All right, so we look here and we look at, we're doing aluminum, right? And for end milling, 0.0 0.05 to 0.01. So let's just say we take 0.05 as our tool feed. Excuse me. I don't know what was on. So a number of teeth would be 2.
Oh, it's my previous.
God, Trevor, but how are we supposed to remember that?
I mean, if you wrote it down.
No.
All right, so let's just get through this. It's not easy. All right, so we got 0.005 because we saw that on the chart, right? That's for FT. Number of teeth is 2 times N, which we solved for the first one, 1900. Still with me? Okay, everybody see where we got those? And now, so the answer would be 19.1. Now, when we take that, we're going to be typing that in with the mill. Okay, so this is, they will give us what is recommended, and then we'll end up doing this to double check that, our feeds and speeds. All right, now let's do it with the 4 flute. All right, so I want you to do this, okay? So we got a 4 flute, 1/2 inch high-speed end mill. So let's kind of walk through it a little bit here. So if we look at it, we're doing aluminum, and our cutting speed is 250. God dang it, this thing sucks. All right, so
we got a different RPM.
Pretty sure I know what I'm on.
what?
You have different slides for each step you have. So like you have the first step, and then the next slide will be the first and second step, and you have the third slide for the first, second, and third. So it keeps like cycling through.
Okay, so it keeps going back to the beginning.
You might want to delete the first few until it's the last.
All right, so we need to first calculate the feed rate, right?
The spindle feed? It's just
Spindle feed,
twice
so we
the
got
speed,
N.
ain't it?
And then we now we got 4 teeth, number of teeth. We've already looked up aluminum, 0.005. And now we go
Stop bleeding.
38.2. Would you feel? Now, all right, do write this down. What are facts that affect feed rate? You got dull cutting tools, you got to modify it. Power of the spindle motor, that won't affect us. We got more than enough power with the Haas. Okay, even if it's designed to mill high-speed steel. Okay, condition of cutting tool, the depth of cut, definitely how much are you taking off at a swipe, and the quality of surface finish required. If you're just trying to hog that out at the beginning, you're not too worried about it, especially you got high speed a bit, you're able to push it a little bit. But then if you need a nice polished finish on your belt buckle, that last one, you might be really cranking up the speed and going extremely slow for a nice polished finish and not doing a great big depth of cut. Rough and versus finishing cuts. A lot of times you'll do a rough, and then at the end you'll come back and you'll do a nice finish cut that you're just taking a little bit out and you're going really high as the spindle speed will take you, and going as slow as you need to. strength of the fixture, whether you can hold that piece in there when you're doing it. Plunge feed rate is how fast you can plunge into something. Like if I gotta go into that metal and I gotta mill this out, how fast am I coming down and plunging into it? And it's typically half the feed rate divided by 2. So that's easy enough. We don't need to do this. It's just divided by 2.
So what's the major complications that come with running at a higher RPM than you need to? Is it just more wear on your tool?
Depending on the material that you're using. And that would be a great question to remember when we go to the tooling room at SMC or something like that, because honestly, I don't have a great grasp of this. I've only been doing it for a year. But from what I see would be unnecessary wear on your tool, because you're spinning, and if you're not moving fast enough and you're just spinning there, you're increasing the friction that you're causing, and so you're increasing the heat, and so that's harder on your tool. You want to be moving at speed that is appropriate to how much you're able to cut. All right, we're not doing this because we're ready to go. All right, so this is a Project Lead the Way engineering formula sheet. All this, and you are to now go into Google Classroom, complete that worksheet as best you can. I'm going to be gone tomorrow, so if you get stuck, you're going to need to be asking yourself, because Mr. Barron's going to be the sub, and I don't think he's going to be knowing how to do speeds and feeds. Okay, so yes.
Is there like a sheet with all the formulas on it, or
The one that we got last year.
is that the engineering?
Engineer formula sheet. We'll have this on it.
I don't know if I can.
Mine's in my binder from last year, because I got home from
But-
school last night, threw it away, and threw it in front of my room, haven't touched it.
That's what I did with all this stuff.
Unreal.
Day before school, I opened it up.
Yeah, I got my glasses from it.
You were driving without your glasses in?
I can drive without my glasses.